welcome you all to this course on defects in material. Today we will be covering transformation of coordinates. Okay. The first question which arises is, why should we study the transformation of coordinates? What is the need for that? This is essentially depends upon the type of situation which we are looking at. There are many situations we have to look at coordinate transformation, because there are many situations where we find that we measure, for example, we measure a property in one coordinate system and then we try to interpret it in terms of some other coordinate system. The example which, if we can take it, is elastic properties of the measure of a single crystal. If you wanted to measure, we may be taking a sample with this external shape. Okay. So the coordinate system which we will be choosing, it is these three as the axis. Okay. But in the sample, the crystallographic coordinate system will be something else. It may be in this particular direction, correct? It's a single crystal. So that means that the property are generally related with respect to the crystallographic coordinate system of that sample. But when we do a measurement, we do it with respect to an external coordinate system, right? Another example is electron backscatter diffraction. When we do, there again, one is a coordinate system of the sample with respect to which, but what are we trying to find out? The plane normals of each of the grain, which we are trying to find out with respect to the crystallographic coordinate system. There also this sort of transformation will be required. The third is stress and strain measurements. When we do, or the stress and strain field around a dislocation, we wanted to find out. Okay, we have a crystallographic coordinate system which is there, okay, which we may be using like Cartesian coordinate system, okay, y and z. But quite often what are, we can choose the system like z, x, y. I'm just marking it like this. And when we choose a dislocation, okay, the dislocation is not line is not lying along any of these coordinates, correct? It is inclined with respect to this. And stress and strain field around a dislocation is described in terms of a coordinate system, where we take this to be the z axis, okay, that is the slip plane, where the bulges vector is there, that is the x axis, and the plane normal as the y axis, we choose it, correct? So this is another example where we have to go from one coordinate to another coordinate. In fact, when we consider dislocation, okay, another transformation which is also necessary is that not only Cartesian, okay, because of radial symmetry, we may have to go from Cartesian to essentially a cylindrical coordinate system, or there are many cases where we'll have to go from Cartesian to spherical coordinate system. This sort of transformation also will be required. And you may be familiar with this transformation from Cartesian to cylindrical, or Cartesian to spherical coordinate system, okay. So what we will consider in this class is one, if you look at it like this sort of two Cartesian system which we consider. One is a rotation of axis which is necessary to go from one to the other, correct? Then another is that the unit cell dimensions itself might have changed. These are all the two cases. So we will consider both the cases, okay. One is rotation of axis. If we do, how that's going to change, how the transformation can be related from one coordinate system, okay, when we rotate it and come to a new coordinate system, how the vectors change. This is one aspect which we will consider. The other aspect which we will consider is that in many transformations, especially phase transformation takes place, the disordered alloy is in one particular phase, and the ordered one is in having another crystal structure, okay. But as far as the atom positions are concerned, they remain the same. So two different types of unit cells we have to consider. Okay, and as you have you have studied in crystallography, okay, the unit cell itself is not uniquely defined. Okay, you can have a square type of a unit cell depending upon the cell, or it could be a parallelogram, or it could be a rhombus, depending upon the situation, the different types of unit cells which we can choose. Then also this sort of understanding this sort of transformation is really necessary. Okay. What we will do it is that let us consider the coordinate transformation, which is essentially rotating from in the Cartesian coordinate system. Okay. So here, if you try to look at it, x, y, z, okay, which is shown in black color, that represents the normal Cartesian coordinate system. Okay. This coordinate system has been rotated to x dash, y dash, z dash. Okay. So when such a rotation has been done, okay, we can make out that from x dash, okay, the new coordinate which has come, it is rotated with respect to the x coordinate by an angle alpha. Okay, it makes an angle beta with respect to a y coordinate of the world system and a gamma with respect to the z coordinate of the world system, correct? So essentially what we said is z dash, and this is alpha, this is beta, okay, and this turns out to be gamma, correct? Now what we are trying to do is that what is the component of x in this direction? What is the component of y in this direction? What is the component of z in this direction? If all the three we take together the same direction, if we add it, we get the value corresponding to that x dash. That's what essentially is written in this equation, correct? So this essentially depends upon the angle between, okay, the axis, okay, what that x dash makes with respect to x, y and z. Similarly, we can find out the angle which y dash axis makes with respect to x, y and z. Similarly, that z what it makes, okay. This is the information which is necessary. Similar way, we can represent the old axis in terms of the new axis also, okay. Then what we are looking at it is what is going to be the projection of x dash onto this x, projection of y dash onto x, and projection of z dash onto x, okay, and all we add together, we get the value of x, y and z, right? That is what we have written here. This is all with respect to the angle between the axes. Fine. In many books you find that instead of using x, y, z, these may be represented as x1, x2, x3. These sort of symbols are also used. That is essentially what I have shown here, okay. And then what I have done it is that this angle I had used suffix that cos alpha x dash x, means that that angle between x dash and x coordinate, okay, that angle is alpha. That's what we are trying to do. Instead of using these symbols, we can just represent them in a nice way in a matrix formation, okay. That is what I had just defined them as A11, A12, like this we can define it, okay. If we try to do this, okay, then these equations will turn out to be x dash will be y dash will be equal to A21 into x, A22 into Y, A23 into Z, Z dash will be equal to A31 into X plus A32 into Y plus A33 into Z, correct? This can be written in a matrix form also. So as a column vector, we can write X dash, Y dash, Z dash. This will be equal to A13, okay. This form also we can write it, and this matrix is the transformation matrix to go from one coordinate system to the other coordinate system, okay. And similarly, if you wanted to find out from transform from, in fact this can, then it can be essentially written as A33, the whole inverse, okay, X dash, Y dash, Z dash. This is the way also we can write it, right? And this inverse of this matrix will turn out to be nothing but a transpose of that matrix, okay. That's what essentially is shown in this transparency, okay. Is this clear? Because this is, here we can write X dash equals A into X, correct? So if we put A inverse multiplied by A inverse on either side, so then this will turn out to be, X will turn out to be A inverse into X, correct? That's what essentially we have done. It's nothing but a simple matrix algebra, okay. Is this clear? Okay. So using these matrices, okay, the transformation matrix, we can go from old coordinate system to new coordinate system, okay, or from a new coordinate system to a old coordinate system, which is essentially just a rotation of axis. Okay. Suppose we have a vector in the old coordinate system, okay, which is just described as the P, okay, and the same vector in the new coordinate system we are describing it as P dash, okay. Like here there is a vector is there, P, the old coordinate system it is P, the new coordinate system it is P dash. Then we can write this, P can have components P1, P2, P3, correct? Similarly, P dash can have components P1 dash, P2 dash, P3 dash, okay. Then these components also exactly similar to the transformation of the from one coordinate system to another, rotation of coordinates which we have considered here. The same way we can do it. So essentially what will happen is that P dash will be equal to P1, A12 into, I am just writing the final result, but you people can work it out. Okay. Okay. Similarly, from the components of P1, P2 in terms of P1 dash, P2 dash, P3 dash also we can work out. Okay. This generally we use some shortened symbol to represent it, okay, where we write P1 dash essentially as is shown here, okay, in terms of sigma. It's just nothing but an addition of 3 terms, okay, and as A1j Pj, that's the way we can represent it, okay. And then if it's like a PAS term, if we do it, we have to take 2 summations will come, 1 over j, then next over I it will come. This can be represented in a simple form like this: Pi dash equals Aij Pj, and wherever the symbol gets repeated, that's that Einstein convention which we use, that is the one over which the first the summation will be we will take, and then the next one will come into the picture, okay. That's it. So what I have done in this slide is that the transformation matrix from new in terms of old, old in terms of new, both for the coordinates, unit vectors ijk, okay, in the old coordinate system and new coordinate system, and the vector components, all of them, what is the transformation matrix which is to be used is given in this transparency, okay. Now we will go to change of from rotation of coordinates to suppose there is a change in the type of unit cell which we choose, okay. This situation we face quite often in phase transformation, okay. Suppose from one particular unit cell which we have chosen, we change to another unit cell, the indices of the directions and the indices of the planes will change, okay. What will be the correspondence between them, between the old and the new coordinate system? That is what we will look at, okay. First, let us illustrate it with an example, okay. Here what I am considering it is essentially a hexagonal lattice, okay. In this lattice, this will be the unit cell, okay, and the x and y axis, both of them, they have lattice parameter is A, angle between them is 120 degree, okay. There are many situations where we can, this could be a situation which can develop. This is just what we have considered is only a 2-dimensional lattice which we have considered. If we keep the same lattice, okay, one on top of the other, a simple hexagonal lattice will be generated, okay. There are situations where they undergo a transformation. One such case which we have considered, where it undergoes a transformation from hexagonal, when ordering takes place, it becomes an orthorhombic structure, okay. Here what happens is that you can look at it that every alternate atom, now they have become, okay, different type of an atom, and the next row nothing has happened, the next row again it gets repeated, the alternate atoms are a different type of an atom. Now if you look at what is the symmetry which this has, hexagonal lattice has got a 6-fold symmetry, that is lost, okay. That's one thing which we can see, okay. Another is that the unit cell here, now it is going to be, this is the type of a unit cell which will be considered for a 2-dimensional lattice, right. If this 2-dimensional lattice is kept on top of it, it will be exactly similar to a disordered lattice which we have considered here. So in such a case, okay, the axis, the new axis, if we can represent it in terms of the old axis, then we can find out information about the planes and directions. Another thing which happens is that in this specific case, which happens in ordered lattice also, instead of every alternate atoms getting alternate atoms are of different type here, it is in this particular direction, close pack direction. It can happen in this close pack direction, or it can happen in this close pack direction also. So there are 3 ways in which this tetragonal lattice can orient itself. So because of that, to know what is the relationship between that old and the new coordinate system, for each one of them is very much necessary to find out the correspondence between the planes and directions. Okay. Okay, here these are all the coordinates, okay, A and B. Okay. There's another type of a transformation which can occur, that six-fold symmetry is retained. Okay. Here if you look at it, every alternate atom in a particular row, if we consider it, okay, they are of the different type. The next row, all atoms are of the same type. Next row, again if you see, it is of alternate atoms, and the alternate atoms in this row are of different type, but they are shifted with respect to this one by half the lattice translation vector here. Okay, so this retains this is also another type of a transformation. Okay, and here if you look at it, though the directions of the axis remain that same, but the lattice parameter is double, correct? So these are all the different types of situations where we have to get information about, okay, a coordinate transformation. Okay, how do we go about it? Okay, suppose A, B, C are lattice vectors of a unit cell, okay, in the new coordinate system. That's all capital ABC, and small ABC is the lattice parameters, okay, in the old coordinate system. Okay, and then the relationship between them is essentially will be, we are writing it as okay, here M1, M2, M3, okay, these are nothing but the projection of this vector A, okay, in this particular direction, right? That is how we are taking it. And these values could sometimes or could always be larger than, because the case which you have considered rotation of axis, okay, there is the cos theta which we considered it. The value of cos theta can be less than 1. Always it is less than 1, right? The maximum value is only 1 which it can be having it. Here, that's between 0 and 1 it will. Here, these values could turn out to be higher also. Okay. The reason essentially is that it will multiple times cos theta will come if the unit cell dimensions are double, correct? That's the only difference which is going to be there in this particular case. Okay. So here, these are all the coordinates of the lattice transversion vectors of the new axis in terms of the old axis which we have defined it. Okay. Similarly, we can consider the old axis, okay, in terms of the coordinates of the new lattice. Okay, and in between these two, I had used two different types of symbols, right? correct? Because the axis, when we consider what we are trying to find out, is in this case, when we look at A, what is going to be the coordinates of A in terms of the old axis system? What is going to be here the coordinates of A in terms of the new system? Okay. When we look at these values, these coefficients need not be the same. They will be different. That is why we are representing them with two different distinct symbols. Okay. Okay. So this can be represented in a matrix form also. Okay. That is what is shown here. Okay. So M is the matrix which is used. This matrix represents, okay, the one to transform from old system to the new system. Okay. Ni used to denote this matrix to transform from new in terms of the old in terms of the new system. Okay. The other one is M is the matrix which is transformation matrix is used to denote the transformation matrix from old to the new system. Okay. Okay, these are all the equation. The relationship between N and M will be, one will be an inverse of the other, the matrix. Okay. Suppose we have to find out the change of direction, like the way we have considered a vector. Okay. This vector can have different types of coefficient, because essentially the vector remains the same, only the coordinates have changed. Okay. How do we represent these vectors? Suppose in the old coordinate system, we represent that vector R is equal to U into A plus V into W, V into B plus W into C. Okay. In the new coordinate system, it's all capital letters. Use it. U into A plus V into B plus W into C, correct? Now, if we substitute for A, B, C, okay, in terms of the old coordinate system, the values, okay, and then what will happen is that M22 into B plus M23 into C plus M31 into A plus M33 into C. Okay. Now, if you take the coefficients of A and B on either side and equate it, then this will turn out to be U will be equal to M11, okay, into U plus M21 into V plus M31 into W, correct? Similarly, V will turn out to be M12 into U plus M22 into V, M32 into W, W will be equal to M13 into U, M23 into V plus M33 into W, right? So this relationship can be used to find out the indices of the directions Suppose we know the indices of a direction in the new coordinate system, then we can find out what will be the indices, okay, of the direction, the same direction in the old coordinate system, okay, which we can write it in this particular form also. So only what we have to see here, what one can make out here is that if it is u, v, w, okay, this, if we write it in a matrix form, this will be nothing but m u. This matrix is nothing but a transpose of the matrix which is used, okay, to go from old coordinate system to the new coordinate system. Okay, that's the only thing which one has to remember. Okay. Similar way, we can substitute for A, B, and C in terms of the new coordinate system. Okay, and then do the same algebra. What we will end up with it is that U, V, W and 3, 1. Okay. Into UVW. This is what essentially it will turn out to be. Okay. Here again, with respect to a coordinate system which we considered, okay, or the transformation matrix which is there to go from new to the old coordinate system, okay, the matrix for the indices of direction turns out to be essentially a transpose of that matrix. Okay. Suppose we wanted to find out the change of indices of planes. Okay. But we know that whenever we represent planes, okay, in a crystal system, we use HKL, Miller indices, to represent it, correct? The way we find out the Miller indices is essentially a way we take an inverse of the intercept which makes in the real axis. That means something to do with a reciprocal lattice. Okay. Actually, Miller indices are nothing but essentially the vector which represents, okay, the plane in the reciprocal lattice, its coefficient. Okay, that's what essentially Miller indices. So same way we can consider the reciprocal lattice. How do we represent if ABC is a real lattice, the whole coordinate system? We can have a reciprocal lattice corresponding to that, and its coordinates are A star, B star, C star. We can take it. Similarly, for the new coordinate system, which is represented by capital A, B, and C, we can have a coordinate system like this: A star, B star, and C star. Okay, and like in the case of a direction, any vector, if we take it, okay, and that vector magnitude should remain the same irrespective of which coordinate system which we choose it. So in that case, R star will turn out to be A star plus LC star equals H into A star plus K into B star plus L into C star, correct? what we can do is that it's just an algebra which we are doing it. If on this side of it we take a dot product of this vector with a vector A in the new coordinate system, then this will become A dot H into A star plus K into B star plus L into C star. Okay, this if we take it on this side, A star into this factor, finally H A dot A star is going to be equal to 1, others will be 0, this will turn out to be H, correct? Here we can represent A in terms of the whole coordinate system, the value which we have. So this will turn out to be M12 into A, M11 into A, 13 into C, okay, dot C star. And here if we take the dot product, what all terms which are going to be there? M11 into H, M1 into K plus M13 into L, this equals H, correct? Similarly, if we take a dot product with B and C also, we will be getting expressions like M21 into H, 22 into K, 23 into L equals K, M31 into H, 32 into K, M33 into L equal to L. Okay. From this we can write it that HKL is going to be V1. This will be HKL, right? What one should notice is that here when we go from the Miller indices in the old system to Miller indices of the new system, okay, the same matrix which we had used, the transformation matrix to go from old coordinate to a new coordinate, the same matrix is coming in this transformation also. Whereas in the case of direction, it turns out to be the transpose of this matrix, correct? Is this clear? Okay. Similarly, okay, we can take, instead of taking with the coordinate of the dot product with A, okay, which is a vector in the new coordinate system, we can take with respect to A which is in the old coordinate system. Then we will be able to find out relationship between, okay, the old coordinate system, that is the Miller indices of the in the old coordinate system in respect of the Miller indices of the new coordinate system, right? And that will turn out to be HKL will be correct. So these are all the only expressions which one has to remember to transform from one coordinate system to another coordinate system, okay. And when we know between planes and directions also, in fact similar relationship can exist between the volume of the unit cell in the old coordinate system and the volume of the unit cell in the new coordinate system. The expressions I had given it in the slide, but I would expect you to derive and verify it. Okay. Yeah. So in this slide, all the expressions which are necessary I had just given in a table form. Okay. Let us consider an example to go from one coordinate system to another coordinate system. Okay. One can take from one transformation from one coordinate system to another, one can take it. That I will give as an assignment. Here what I will consider is to go from hexagonal to an orthorhombic system. Because why we have to do it? Quite often we find that when we are using a hexagonal system, okay, 3-index system is not convenient. We go for a 4-index system, okay. But we are more used to using a 3-index system, right? So if you make a unit cell, which is essentially, because as we have discussed earlier, okay, unit cell is not unique. Even for a hexagonal lattice, we can make a unit cell, okay, which is essentially a orthorhombic type or a rectangular type of a unit cell. Okay. Let us consider such a case. In this particular case, if you consider, this will be the A with respect to a hexagonal lattice. Okay. This is the B coordinate. Okay. And assume that the next layer is just sitting on top of it. Okay. It generates a simple hexagonal unit cell. Okay. And this can be considered in this particular way also a unit cell with a centered one atom at the center. Okay. And A becomes the lattice parameter for this, and B is the lattice parameter for in this particular case. Now what will happen in this case? If we try to represent A in terms of the volt system, A will be equal to, okay, 2 times A, correct, plus B, correct. So this will be 2A plus 1B plus in the yeah, plus 0 into C, correct. What will be B? 0 into A plus 1 into B plus 0 into C, correct. What is C going to be? 0 into A plus 0 into B plus 1 into C, correct. So now if you write it in a matrix form, this ABC will turn out to be 1, 0, this is right now, okay. So this is the from old coordinate system to the new coordinate system, we can get that information. Okay. Similarly, when we wanted to represent A in terms of the new coordinate system, How we will represent? A will be half into A, correct? Half into, right? Minus half into B plus 0 into C. B will be 0 into A plus 1 into B, correct? Plus 0 into C, correct? And C will be 0 into A plus 0 into B plus 1 into C. So this A, B, C will turn out to be half minus half, 0, 1, this is right. So these are all the relationship to go from one coordinate system to another. Once this relationship is there, okay, using the formula which we have written to go from directions as well as in the planes, okay, we can immediately find out what is going to be the correspondence which it will be there. If it is take a vector in the old coordinate system, what will be the direction in the new coordinate system, okay. That we can, because suppose it's the u, v, w. If a vector is there in the old coordinate system, okay, in terms of the new coordinate system, M32, M33, U, V, W. This matrix, okay, is nothing but this one, correct? So we can use this to find out, okay, if you know the vector, what it's going to be. Similarly, if you wanted to find out a vector in the old coordinate, new coordinate system, in terms of the old coordinate system, then we have to use the transpose of the matrix, okay, or the not transpose, the inverse of that matrix, and then we can find out. Okay. This you can take some directions, okay, take an example and work out for yourself, okay. So essentially in this lecture, what I have tried to do is to derive expressions, okay, to go from one coordinate system to another coordinate system, okay, if that coordinate system involves only just a rotation of axis, and another if the coordinate system is essentially changing from one lattice to another lattice, where it's not only just a rotation, even the dimensions of the lattice parameters change, that's the volume of the cells also change, okay, both the cases which we have considered. In this particular case, I had given or I had just mentioned about it that one can go from rhombohedral to hexagonal. Similarly, the primitive lattice for FCC is rhombohedral, okay. Similarly, primitive lattice for BCC is rhombohedral. So one can transform from one to the other and vice versa also, how to go from that. This one can work out as an assignment. When you do that, then these concepts will become much clearer, okay. And similarly, as I went to a class talk about how the stress field and strain field around dislocations are calculated. Okay. In that case also, okay, you will understand what is the need for going from one, that's crystallographic coordinate system, which is essentially a Cartesian coordinate, to another Cartesian coordinate system, which is nothing but rotation of the axis. Okay, I'll stop here now.